What you are seeing right now is not an artist's imagination. This is a revolution in the history of physics. It's the real-time visualization of the very moment a quantum object behaves as both a propagating wave and a particle simultaneously. For the first time, this property, which we could only observe in separate time frames for years, has been captured at the same instant. A group of physicists from the Swiss Federal Institute of Technology in Lausanne, EPFL, has achieved the seemingly impossible by using nanotechnology and ultra-fast electron microscopes to film this strangest feature of quantum mechanics. Today, we will examine how these scientists performed this incredible experiment. Fasten your seatbelts. We are diving into the quantum world. We can imagine this magnificent duality in the nature of quantum mechanics like this. Sometimes, it behaves like the ripples from a stone thrown into a calm lake, acting as a wave. In this state, when it encounters an obstacle, it elegantly bends around its edges, almost hugging it as it passes. At other times, it forgets its entire wavy nature and behaves like a tiny marble locked on its target. In this state, it finds a narrow gap in an obstacle and passes straight through it, without any deviation. So, how do these two different properties fit into a single frame? In the world of classical physics, think of a vehicle with two features: an amphibious device. It can travel on both water and land. However, we cannot see both of these features at the same instant. An amphibious vehicle cannot be in the sea and on land at the same exact time. This is very clear to our intuition. But when you come to the quantum world, an electron can act as both a particle and a wave at the same time. Now, let's look step by step at how this ingenious experiment works and how that famous secret of quantum mechanics was visualized. You're currently seeing a macro-scale arrangement of the experimental setup. First, a nanowire is placed in this vacuum environment. Subsequently, a laser capable of firing pulses at femtosecond intervals, that's a quadrillionth of a second, is activated, and the laser is fired. To understand what the laser does, let's look at the concept of a surface plasmon. The surface of this silver nanowire is full of free electrons. Think of these free electrons on the wire surface like a row of birds sitting on a power line. Let the laser beam be a faint sound that reaches them. Just as the birds take flight and resettle as the sound reaches them, these electrons on the surface of the wire begin to oscillate all together in a regular pattern. This collective electron oscillation is what we call a surface plasmon wave. The purpose of the laser here is to create a plasmon wave from the free electrons on the surface. The laser, continuing on its path, strikes the free electrons on the silver wire, causing them to form a regular wave. This colorful pattern you see beside me right now is that very surface plasmon wave created by the laser exciting the electrons on the silver wire. The secret to obtaining such a pattern is the laser's own regular, synchronized structure, which can apply a synchronized impulse to millions of electrons at the same time. The laser's wave forces the entire sea of electrons to move back and forth in unison, like a giant choir. This collective, synchronized dance of electrons creates the surface plasmon wave we see. Immediately after the wave appears, electrons are fired from an electron gun above. The purpose of this electron is to provide us with data based on the information it gathers. To understand the experimental design, we have visualized a single electron here, but in reality, millions of electrons are fired and their measurements are taken. Since the entire experiment is based on the electron microscope measuring an electron's energy, let's first look at how this measurement is done in a very simplified way. Electron microscopes are devices that can apply a magnetic field to electrons and measure their position. A known magnetic field is applied to an electron within the microscope's scanning area, and we observe how much this field deflects or drags the electron. For example, in a situation where we apply a units of magnetic field and detect an electron that deflects 2x units. If another electron deflects x units when given the same units of magnetic field, we can say the second electron's energy is 4 times the first, because the relationship between its energy and deflection is squared. You might ask, how do they know how much the electron deflected? When the electron passes through the magnetic field and completes its journey, it strikes a special fluorescent screen. When a high-energy electron hits this screen, just like an old cathode ray tube televisions, it creates a small, instantaneous flash of light at the point of impact. This is how its deflection is detected. So if you ask how this image was made, The electron-centric data collection process is based on the energy exchange that the electron sent from the top of the setup enters into with the plasmon wave. Let's think of the plasmon wave as water waves on a surface. The fire electron is like a tiny speedboat passing over these waves at full speed. As the electron, our speedboat, passes through the plasmon's electric field, if it goes through a strong push from the wave's crest, it gains energy. If it passes through a pull from the wave's trough, it loses energy. However, this energy exchange is not random. This is where the quantum rule comes in. The electron can only exchange energy in unit packets, or quanta. In essence, the boat either gets exactly 1 unit of push or 2 units, or 3 units, but never 1.5 units. This is precisely the data the electron collects. Think of it this way. The electron's starting speed, and therefore its energy, is known. Let's say its initial energy is 4x. Then, the electron travels down the length of the silver nanowire. When its journey is over, its energy, again measured via its speed, is 6x. In this case, we can say the electron gained 2x units of energy during its trip. Since the environment is a vacuum, and we know the only other thing there is the plasmon wave, we can say the electron took this energy from the plasmon wave. Furthermore, a quantum object can only exchange energy in quantum packets when it exhibits particle properties. If you detect such a situation, you're talking about quantum objects that have shown particle behavior. So, how is the wave property measured? As electrons pass over the plasmon wave, many more electrons gather at the crest of the wave, or electrons can exchange much more energy there. This means if there are many electrons in one place, or a lot of energy exchange is happening, we can say that is the crest of the wave property. Counts taken with the electron microscope also show that while there is much more electron energy exchange in some places, there is much less in others. Think of it this way. No surfer can gain speed from the dampened waves near the shore. But when they go out and catch a big wave crest, they get a huge push energy. That is exactly what happens in the experiment. Yes, the image that has been wondered about for years is now on the screen. First, let's state that we have simplified the content a bit to explain this visualization. We are reading this image based on the electron's position and energy information. The horizontal axis shows how much energy the electrons exchanged. The vertical axis shows the electron's spatial position, that is, where it is on the nanowire. We read the number of electrons from the colors. Red represents the highest number of electrons, while blue represents the lowest. The blue area in the middle is where electrons did not exchange any energy. For example, we read point X on the screen like this. At this point, there are 50 electrons, and all electrons at this exact position have gained 2 electron volts of energy. And this point X is located at the 0.35 micrometer level of the silver nanowire. If you notice, the energy exchange of the electrons is concentrated in some regions and sparse in others. But whatever the value, this exchange is discrete, that is, at exact values like 2 or 3 electron volts. This shows us that the electron does not exchange energy continuously, but only in specific steps. This is direct proof and visualization of its particle property. So, where's the wave property in this picture? Let's return to position X and draw a line across the position space axis. As you can see, we see repeating colors, meaning different numbers of electrons that correspond to this line. For example, while there are 50 electrons at point X, there are 25 electrons at point Y. When we come to point Z at the same position, there are, for example, 15 electrons. And we know that high electron counts occur at the wave crests, while low electron counts are in the troughs. This visualization, therefore, also shows us the wave structure of the quantum object. Science lovers, today we brought you an unbelievable experimental design and an article that explains what kind of world we would see if we could perceive the quantum world with our own eyes. If you noticed, we didn't mention when this experiment was conducted. When do you think this experiment might have been done? Let's discuss it in the comments. To help spread science, you can subscribe to our channel, like our videos, and press the join button. See you in our next video.